In this video we're going to talk about variational principles. Now variational principles pop up in all areas of mechanics really, and so will crop up all over continuum mechanics as well. And they were originally developed for something called Lagrangian mechanics. And let me just go back a slide there. Lagrangian mechanics is all based around this quantity called the Lagrangian. Now the Lagrangian is defined to be T minus V, where T is the kinetic energy of the system and V is the potential energy. And we further define something called the action. And the action is a functional, and I'll talk about what that means in a second, of the position of the particle x, which is a function of time. And this functional is equal to the integral between the initial and the final time of the Lagrangian, which is itself a function of this function, and also maybe of its time derivative, and also potentially of time itself, integrated over time. Now, a functional is basically a function of a function. And the key thing in Lagrangian mechanics is something called the least action principle. And this states that the system will take a path. So the system will take a path x of t that minimizes the action. And this is the founding thing behind Lagrangian mechanics. So how do we minimize S? It would be really easy if S were a function. We've got tools for minimizing functions. We've got calculus. We take derivatives and we set them equal to 0 and find maxima and minima. What do we do for S? Well, this is what variational principles is for. It's about finding stationary points of functionals and the functions which make them stationary. So the key concept here that we're going to talk about is a so-called functional derivative of S. And so let's derive that in a simple case. So let's consider this action here, where we're just dealing with a one-dimensional, not a vector anymore, just a function y, which is y of x, and here this y prime is just dy dx. So we've got a functional that is dependent on some functional itself, f of y, y prime, and x. Now, in the same way that when we took derivatives, if you remember that dy by dx can be defined to be the limit as epsilon goes to 0 of y of x plus epsilon minus y of x all over epsilon, is there an analogue that we can take here? Well, let's consider s of y plus delta y and see what that's equal to, where delta y is some function. And we'll talk about boundary conditions in a second, but if I just write this out now, and we see what we can do with it. So usually this function y has, say, fixed ends. We'll consider it having fixed ends, so y of a and y of b are fixed. And we'll just box that here because that's important. And because y of a and y of b are fixed, and we still want to consider y plus delta y is another function that might work, we need delta y of a equals delta y of b equals 0 by star, just to maintain the same boundary conditions. So okay, let's Taylor expand this function inside the integral to first order in both delta y and delta y prime. So doing that, we're left with what we started with in the first place, plus these first order terms, all in an integral here. So we've got delta y df by dy, evaluated at y, y prime and x, evaluated the original variables. And we've got delta y prime df by dy prime, again evaluated at the original variables dx. So we're going to call this thing here delta s, such that s of y plus delta y is equal to s of y, that's this thing up here, plus delta s. Right, so delta s is equal to ba delta y df by dy dx plus, and we're going to integrate this by parts, so we have delta y df by dy prime evaluated at the endpoints, but this is 0 because delta y is 0 on the endpoints, minus ba delta y d by dx of df by dy prime dx. So this is therefore equal to ba delta y df by dy minus d by dx of df by dy prime dx. So for arbitrary variations, therefore, we're left with the so-called Euler-Lagrange equation. Df by dy minus d by dx df by dy prime equals 0, implies and is implied by delta s equals 0. So this here is the Euler-Lagrange equation. And this is the equivalent of finding a maximum or a minimum of a function. If you can find a solution to the Euler-Lagrange equation, it will be an extremum of the functional. And this is incredibly helpful in an awful lot of problems. So Euler-Lagrange equations in general, if our functional, if we had s of y, for example, has some f of y, y prime, y double prime, y triple prime, etc., and x dx, the Euler-Lagrange equation in this case would be df by dy minus d by dx df by dy prime plus d2 by dx squared df by dy double prime minus d3 by dx cubed. And this alternating pattern just comes from doing integration by parts the requisite number of times. We obviously need more stringent conditions on y in this case so that the boundary terms drop out, but you can derive this in exactly the same way. So that's the Euler-Lagrange equation for this more complicated case. You can very similarly derive Euler-Lagrange equations for multivariate functions that might not just depend on x, using exactly the same approach as I took earlier. So key point, no matter what you're given, you take s of y plus delta y, and we'll just write those as vectors to be most general, and Taylor expand to first order, and you integrate by parts. And that will get you the Euler-Lagrange equation for whatever functional that you're dealing with. Okay, so that's most problems solved. But we haven't solved constrained variation problems. And constrained variation problems are where we might have some functional that we want to minimize or maximize, plus a constraint on y. Now, what do we do with maximizing or minimizing functions? And we'll see if we can find an analog in functionals. And the answer to this, if you haven't seen it before, it's probably worth looking this up. So you use Lagrange multipliers. Lagrange multipliers encode a constraint. So we can have something like, if we wanted to maximize f of x equals x squared subject, or x squared minus y, so we'll make it a two-variable function, subject to x plus y equals 3, what we'd have to do is actually consider the function x squared minus y minus lambda x plus y minus 3. And if we want to find a minimum here, we're finding a minimum in x, y, lambda space, because df tilde by d lambda equals 0, which is a condition for an extremum, just comes out to give x plus y equals 3. So can we use Lagrange multipliers with functionals? The answer is yes. So we just add a Lagrange multiplier inside the integral. And the best way to show that happening is probably with an example. And so the next slide has an example here. We're wanting to extremize this functional. So we want to find psi such that I is max or min, subject to this normalization condition on psi. Okay, so what's the functional we need to consider? We're going to modify it with a Lagrange multiplier, and this is going to be equal to psi prime squared, so the original functional, just like we had last time with the original function when we put a Lagrange multiplier in, and then we're going to add this Lagrange multiplier function of x, psi squared minus 1 dx. And we want to extremise this now. So this here is our f of psi prime, and x. So the Euler-Lagrange equation in this case is df by d psi minus d by dx df by d psi prime equals 0. Okay, let's plug all this in. We get 2x squared psi minus lambda of x psi, or 2 lambda of x psi, minus d by dx of just 2 psi prime equals 0. So that gives us this differential equation, psi double prime is equal to x squared minus lambda psi. And that's our answer. Now obviously we haven't solved this for lambda. If you want to see, this question is on example sheet 2 of Variational Principles, which is a part 1b course. You'll be able to find that example sheet online. And so if you want to practice, that question then holds your hand to actually find a specific form of psi. But this just summarises how you would modify the functional in order to solve for a constrained variation problem. Now I've hinted at Variational Principles 1b there, and if you want to find out any more about variational principles, or this is an area you're not particularly comfortable with, I can recommend these notes that are available for free online for the Part 1b course. You mostly just want to look at the sections on Euler-Lagrange equations. I wouldn't worry too much about the second variation or any of the stuff about functions. We're just dealing with functionals here. But if you've got any questions, drop me an email or bring them along to the in-person session.